Hello, everybody. I'm Aldo Di Carlo, Director of Institute for Structure of Matter of the CNR, and I'm chairing this session for the award ceremony of PRISM Prize 2022. It's an honor to have Stefania Cacovich and Riccardo Comin as winner of this prize, and let me introduce the prize, and then we move on with the talk of our winners. I will briefly introduce you our institute. Our institute has 4 main sites where we develop science of matter and technology of matter, and we understand the complex system, and we study complex systems that are made by new form of materials, new device, and all the concepts that are enabled by materials and the combination of different materials. We are focusing in several areas, and we are very taking in consideration that our study should also be sustainable and should also consider the sustainability problem that we are facing nowadays. The institute is quite large. It has 125 employees between researcher, PhD, and postdoc. So what we do? So we do research on structure of matter for different branch and different applications. We mainly focus in the area I show right now. So we have a particular attention for the blue sky research, what could be a research that will introduce a breakthrough as the two scientists that received the PRISM Prize today. But then also we take care about application like biohealth, cultural heritage, ICT and security, energy and environment, and automotive and space. And researchers of the institute are involved in projects that are focusing on these fields. How we do the research? The research is supported by a technology platform, and the technology platform of ISM is called TEMPISM. In the technology platform, we have 4 lines: the theory and models, synthesis, analysis, and prototyping. So this backbone, this infrastructure offer to researcher of ISM and collaborators of ISM more than 130 services and techniques to analyze material, to develop prototypes. We are really focusing on the multi-scale concept. The multi-scale means that, we can consider characterization, for example, from lab scale to a large scale characterization, like the one in synchrotron in Electra, where we have as institute for 3 lines. And this also for device and system. So, for example, we study 2D material at the nanoscale on the surface, for example, but then we use this 2D material for application like solar panels. So this is in short the introduction to the institute. And let me spend a few words about the prize, the PRISM Prize. So how does it work? So we open for a call of nomination. So we ask scientists working in the field of structure of matter to submit their nominations for research who have distinguished themselves for their breakthrough achievement in the last 5 years. So it's not a prize to the career, but it is a prize for active scientists that have made some breakthrough achievements in the last 5 years. After the nomination, we have an international jury that rank and select the winner. So the international jury is composed by those who have won the PRISM Prize, together with the site coordinator and 10 PRISM coordinator of the institute, and they select the junior and senior winners. What is the award? So the award is, beside the prize, the institute offer to the winners the possibility to undertake a direct collaboration with researcher or in one of the topic of interest, exploiting the know-how and the infrastructure of ISM and fully supported by ISM. As you can see, is a very practical prize that we offer collaboration, and so to even further develop and to even further achieve breakthrough in the field of structure of matter. Today, we have the Commission selected two scientists, Riccardo Comin for the senior category and Stefania Cacovich for the junior categories, and the jury was unanimously assigned among all the other this prize to these two winners for their breakthrough achievement in the field of structure of matter, of science of materials. So it's an honor for us to have them here, and I give the floor to them for starting the presentation. So we will have 25 presentation for each of them. Then we have 5 minutes for some short question. So the first is I think Stefania. Stefania, welcome and congratulations.
Yes, welcome. I share my presentation. Hope it will work, as we already tested. Okay. So you should be able to see my screen, I hope. Yes?
Yes, we see.
Okay.
But not in presentation mode.
Not in presentation mode?
No.
Oh, no. That's weird. Wait. We also try it. Yes, presenta. Now, is it in presentation mode?
No, we cannot see now. Just a moment, it's coming. Yeah, it's in presentation mode now.
Okay. Okay. So, first of all, thank you for these awards. Thank you to the CNRS and in particular to ISM. Thank you, Aldo, for the introduction. So today, I will talk about the work I've done during the last year of my career. And it will be about multidimensional photoluminescence analysis for photovoltaic materials and devices. I will start with a short introduction, first about myself. So I've studied at the University of Trieste. I've done a bachelor and a master degree in materials and process engineering there. Then I moved to the University of Cambridge for a PhD in material science. And there my research interest was mainly focused on electron microscopy studies of allied perovskite solar cells. And I will be back later in my presentation about this class of material and this kind of solar cells. And finally, I moved to France to work at IPVF. That stands for Institut Photovoltaique Île-de-France. First as a postdoc, then as a Marie Curie Fellow, and now as a permanent researcher at CNRS. Just a few words on the Institute. IPVF is an initiative that was launched by the French government in 2013 and physically moved to the Paris-Saclay Research Campus since 2018. It's a collaborative solar cell research platform, so we are doing research only on photovoltaic, and it's a public-private partnership. So there are public actors such as the CNRS, that I would say is the French equivalent to the CNR, but also companies that work in the energy industry, such as EDF or Total. And is a center for both research and industrialization. This goes through several programs that go from market assessment to development of tandem technology. For instance, perovskite and silicon solar cells, 3-5 material on silicon, but also a lot of more fundamental activity. For instance, a program on characterization and modeling, and another one on new concept for high efficiency photovoltaic conversion. But how does a solar cell work? I don't know if in the audience there are many people that work on this kind of material, on this kind of technology. So how does it work? A solar cell needs to answer to 3 fundamental functions. The first one is to absorb light. And so every semiconductor has a specific energy gap. So all this part of the solar spectrum will be absorbed. Then once the photon absorbs, we need to avoid non-radiative recombination, and therefore to extract as much energy as possible. And the third one is related to the carrier transport to the electrodes. And so if we're thinking about physical properties to the carrier mobilities, how does this is reflected in the real world? So this is a chart that I think every person working in the the material scientist or physician or engineer working in the fields of solar cells is very familiar with. It's a chart that summarizes all the PV technologies over the years, their evolution in the last 40 years as a function of their efficiency. So each color corresponds to a different generation of solar technology. So for instance, in blue, we have the crystalline silicon cells that are the one that everyone knows is the most employed technologies. So you can see that we go up to 26-27% of power conversion efficiency. We have thin film technologies, for instance, CIGS of cadmium telluride solar cells that also can exceed 20% of efficiency. And then starting from the early 90s, we have another family of solar cells that are generally referred as emerging PV. That includes dye-synthesized solar cells, perovskite solar cells, organic solar cells, and we can see that their evolution has been quite fast. And we go up to 24-25% now for perovskite solar cells, and in tandem configuration we can exceed 31. Actually, now the record has been recently updated. I think now we are at 32.5. But really, the evolution is very fast, and every 6 months this chart needs to be updated. So perovskite solar cell is what I'm working on. This kind of technology presents some very important advantages. One of them is the sustainability, the low cost, the possibility to work in tandem application, for instance, with silicon, but not only, and also their transparencies. Indeed, we can tune the optical band up according to the chemical composition. And this is a point that is particularly relevant for the field of built integrated photovoltaics. However, researchers also need to face some limitation. For instance, the poor stability with respect to external stresses, and this also is reflected in the high hysteresis on IV characteristic. So, what we can do to try to improve the stability of the devices? So, the key factor that has been identified are, on one side, the local chemistry and how the local chemistry affects the optoelectronic properties of the device. They both affect the long-term stability of the device. But let's go a bit more into the detail of this technology. So here I show you the schematic of an archetypical perovskite solar cells. So we have the absorber that is sandwiched between some hole and the electron transport layer, and then we have the two electrodes where the charge and then extracted and transported. One strategy that has been proposed to improve both power conversion efficiency and long-term stability is to work on the interfaces of the absorber with the transport layer, and more specifically to add an interlayer at this interface to passivate the interface and therefore to reduce the non-radiative recombination. However, the system is quite complex because the absorber as itself as a complex chemical composition. We are talking about a family of hybrid organic inorganic materials where this is the chemical structure. So we have a structure ABX3, this is a structure of perovskite, and in the case of halide perovskite, A is can be a monovalent cation, so metalliammonium, formamidinium, or also cesium in the case of fully inorganic solar cells. Then we have another metallic cation, and finally an halide anion. And I was telling you that to improve efficiency and stability, a certain variety of interlayers are introduced at these interfaces. This can be, for instance, 2D materials. Some of them can be other kind of perovskite, but also organic cations or self-assembly monolayers. So what we need to do in order to fully exploit the potential of all this strategy is to deeply understand the chemical and physical phenomena underlying this improvement. So this is what I do. And the characterization method I'm mainly working on are based on multidimensional photoluminescence imaging technique. So in our lab, we have several luminescence imaging technique. Today, I will talk mainly about two of them. The first one is a hyperspectral imager that is absolutely calibrated. We'll see later why the fact that it is absolutely calibrated is so relevant. It allows to acquire three-dimensional data set, two being spatial and the third one being spectral. And it's an optical microscopy based system, so the maximal spatial resolution is about 1 micron. We have then another setup that is time resolved. So it's a film, a time resolved fluorescence imaging setup. In this case, the cube are the dataset are still cubes, so they are three-dimensional. But in this case, the third dimension is time. And so this allowed to acquire maps, and to each pixel of this dataset, we can associate a time-resolved decay. So this is an example of a TR-film acquisition. So here you see, this is a triple cation double allied samples, satin film just deposited on glass. Here we are following the time resolved decay, and here we have the local PL profile. But on top of that, we also have some large area imaging system. Here I show you a couple of papers that came out this year. Some of them were also in collaboration with the CNR. And here you can see that we also image at large scale. So not only really on a small area, on the micrometer size, but also when we go to modules to study, for instance, the homogeneities of this deposition process also for upscale devices. But on top of that, we also work on the modeling. So what we try to do is really to obtain map of physical parameter. So for instance, we can extract many information from a PL spectra. The intensity of the PL is related to the quasi-Fermi level splitting, the PL position to the gap of the material, the high energy tail to the carrier temperature, and this is particularly important for hot carriers or size, for instance, and the low energy tail to defects or disorder inside our semiconductor. How we can locally quantify this parameter? By fitting pixel by pixel the calibrated data by using generalized Planck law. I will show you later some of these maps. But also on time resolved decays, we can try, also from this kind of decays, we can try to fit different parameters. However, this is a quite complex system, a quite complex question to answer. Why? Because often in the literature, to fit this kind of decay, there are used fitting custom function, so B exponential or 3 exponential model. In this case, the fitting is quite easy, but on the other side, the parameter interpretation can be quite difficult because these fitting parameters have not a strict physical meaning. It's also possible to using drift diffusion models. In this case, the parameter interpretation is quite easy because they are based on physical models, but on the other side, the fitting can be quite challenging. First, because there can be some connection, some relationship between the different parameters that therefore they are not independent. And also, if we want to apply such kind of models on a map, so by fitting 1,000 on pixel, this is computationally too heavy. So what we proposed was using a scaling law that is based on drift diffusion models, but that allows for easy fitting and parameter interpretation. So just a few words. This is a work that was done mainly by Guillaume Vidon, that just discussed his PhD thesis. So basically it started from drift diffusion equation, but then what he has done is to work on the derivative on the PL decay a very short time. In this way, he could solve a order one polynomial expression in laser fluence. So this allows to simplify the fitting, as we have this scaling law, and from the intercept and the slope of this scaling law, we can access to different physical parameters. And this is finally to obtain a map of the top surface recombination velocity of a thin film, of also an ODA interface. And finally, I will show you a work where all this concept, all these methods, and also all this technique of data analysis were applied. This is a publication that came out last year. So here, what we wanted to study is a dual interfacial modification of inverted perovskite solar cells. So basically what we wanted to do was to compare a reference cell. Here we have all the photovoltaic characteristics, figure of merit for this cell, and then by adding this organic cation at these two interfaces, we obtain a boost of cell performances that went up to 23.7%. And this is one of the highest values ever reported for an inverted solar cell architecture. So it means we have a PIN architecture with record VOC. So what we try to understand is how the introduction of this cation has modified the physics of the interfaces, and also if the deposition was homogeneous over the surface of the absorber. So to do this, we went layer by layer, because this is also one of the advantages of this technique. They are contactless. Therefore, we can use them at any stage of the fabrication of the solar cells. So we can study the bare absorber, but then we can add the different interface and quantify the non-radiative losses at each of these interfaces. So we started from calculating the quasi-Fermi level splitting of just the absorber, and then we compare this with the value of half cell and finally of a full cells. So if we compare these two columns, the variation between the reference and the passivated samples are not so high. But if we go to the second interface, here we can notice that we have a real improvement, because here the non-radiative losses are reduced in several tens of millielectron volts. And then if we compare these values with the VOC of the devices, we can see that there is a good agreement between the optical and electrical characterization. So here we have a schematic of all optical and electrical measurements. These are the theoretical, the radiative limit that we have calculated for the two. So you can observe that already just with perovskite on glass, we have significant reduction in comparison to the radiative limit. And we can see that for the full devices, this is even higher, because when we add an interface, we are also losing energy. And here we have a summary of all the measurement we have done. So we have a good agreement, as I mentioned before, on optical and electrical measurement. And also we can say that the main losses occur at this interface. And finally, I show you the maps I was mentioning before. So on both delta mu and here we have Urbach energy, that is another parameter that is related to the defects of our material. Here we just correlate pixel by pixel the gap, the variation of the gap as a function of the variation of the quasi-Fermi level splitting and of the Urbach energy as a function of quasi-Fermi level splitting. We can see that the distribution are not so wide. So this means that the properties of this material are quite homogeneous. We can see there is a pretty much uniform coverage of the 3D perovskite, because here we can see that there are only small variation of these values, and that the energy gap and Urbach energy are constant after the addition of the active ions. Then we did the same analysis, but for time resolved experiment on half cell and on full cells. And again, what we observe is that the real improvement is after we added the transport layer. This means that these processes are not just, it doesn't mean that there is only a surface passivation, but rather an interfacial passivation. And these are the maps of the decay time. So we can note that the decay time has improved all over the thin films. And we also calculate the surface recombination velocities at top and at the bottom, and we can see that there is an evident reduction in terms of recombination velocities. With this, I think I've finished my presentation. So let me acknowledge all the people that are working with me at IPVF, but also our collaborator at the University of Pavia for this work on passivated inverted perovskite solar cells, and also the work we've done in collaboration with the CNR and the CHOSE laboratory, and European Union for funding Memory Curie and City Solar project, where I'm working right now. And thank you. And if you have any question, I will be happy to answer.
Thanks a lot, Stefania, for very interesting, incredible results you achieved in this period. And before going to the questions, I'm waiting because we are a little bit delayed for the questions. So it's a very honor for all of us, I mean, to have the president of National Research Council, Professoressa Maria Chiara Carrozza. Please, Maria Chiara.
Hello, good morning, good afternoon to everybody, and it's a pleasure to attend this presentation and by Stefania and by Riccardo related to this important award and competition that is organized by CNR and the Institute of in English. How do you translate your acronyms? I don't know.
Structure of matter. Very direct.
Institute of matter.
Structure of matter.
And I'm joking. It's a pleasure. And so, first of all, congratulations. And for this important achievement of your careers, and also for your profiles, because I had the opportunity to see who you are, and your achievements in research are impressive. And so you know that we are organizing and reorganizing the National Research Council in order to be attractive for young researchers, for young leaders. We want to be very open and welcome researchers here, and we are trying to develop infrastructure for being a very good environment for developing leaderships. So I hope that you, Stefania and Riccardo, will develop your leadership and also your dreams in research. It's important to have personal dreams, and I think your presentations and your careers already demonstrate that you have your dreams and your objectives and your goals. So congratulations again, and I would be happy to meet you in person, I hope, because I don't like so much to meet virtually. I am for physical meetings and with social relations, because I think research needs also some personal exchanges, very free and very open. So I hope that Aldo and colleagues will organize meetings for meet everybody and try to establish a connection. So thank you very much, and go on with the presentation by Riccardo, I think.
Thanks a lot, President. It's really a pleasure. So we catch your suggestions. So we invite Stefania and Riccardo in our laboratory so we can start immediately the research collaboration together. And okay, and Stefania, there is a comment about your presentation. Mainly is related to the recombination, and so you show that you can capture clearly the recombination with your technique. Is it possible to distinguish between interface recombination and bulk recombination, and where is the source of recombination that limit the VOC of the system?
Yes, it is possible with time resolve measurements, and for doing this, we treated the time resolve decay with some model, and this allowed us to obtain a map of surface and bulk recombination. So we are able to locate where the recombination are and also to quantify them. Yes, this is possible.
Okay, I think there are no other comments for the moment. So thanks a lot, Stefania. And now let's move to the talk of Riccardo Comin. And Riccardo, please, the floor is yours.
Thank you, Aldo. Let me see if I can get my screen place. Okay, can you see the full screen? I can't hear anything, so I'm assuming it's working fine. Okay, so let me start by thanking Aldo and Maria Chiara for the introduction and also for the very kind words. And it's a true honor to receive this prize, and it's also a great pleasure to be here to have the chance to talk about our research in front of your community and in front of your institute and this audience in particular. My talk is sort of like a very hardcore experimental condensed matter physics talk. Is very much on the front of fundamental research, and the title is Singular Bands in the Kagome Lattice Superconductor. So I will talk about some materials realization of a particular type of lattice, which is called the Kagome lattice, which is the one you see here in the background of my cover slide. And my talk will in particular focus on the description of the electronic band structure of the Kagome lattice, and more specifically about some special points in that electronic band structure where the electrons behave in a singular way. I will tell you in a bit what that means, and how we believe that underlies the exotic properties of these systems. So let me start by giving credits to the ones who really deserve it, and that would be Minggu Kang. Minggu is a sixth-year graduate student in my group. He's an extremely talented young scientist who's been doing essentially all of the experimental work that I will show in my talk. And he's been working closely with Shang Fang, who's a theorist, condensed matter theorist, and he's been really the main engine behind the development of all the band structure theory to understand these materials. Let me actually maybe see if I can put a laser pointer. Okay, this should be better. Yes. And then we have done this work at synchrotron facilities, not Elettra, as it turns out, although we have done similar measurements on different projects at Elettra. But we worked at the Advanced Light Source and at the Pohang Light Source in South Korea. And we have worked on crystals from the group of Stephen Wilson, University of California, Santa Barbara, and we have a close collaboration on the theory front with the group of Giorgio San Giovanni at University of Würzburg and Tim Kaxiras at Harvard. So let me start with a hopefully, not too long introduction on quantum matter, although this is, of course, very important as an underpinning of the rest of my talk. So what we mean by quantum matter, like you might have heard this in different contexts. It's become almost like a buzzword, like quantum materials, quantum solids, quantum matter. So my understanding of what really quantum matter means is it means the realization of phenomena where quantum mechanics is really needed to understand things, not just at the atomic level, but at the macroscopic level in a given material. So in the beginning of the 20th century, we had the first quantum revolution where quantum mechanics was developed, and it was developed in particular thanks to the effort into the understanding of the atomic structure in solids, so the atomic physics, and what we can essentially call one-body phenomena, where we have one electron interacting with one atom, and we're trying to understand the energy spectra of that simple system. But then, of course, in real materials, we put together a large collection of these atoms and electrons, and then there are additional emergent phenomena that can happen. This is what we call collective quantum phases of collective quantum phenomena. And there are many, many different flavors of these because they really depend on the ways that the electrons interact with each other. And so a very common mechanism, in collective electron phases is what's called electronic symmetry breaking. So what happens is that the electronic degrees of freedom, the charge, the spin, and the orbital degrees of freedom break the native symmetry of the host lattice. And they can do so in many different ways because there are many, many different possibilities. You can have magnetic order, so you can have an ordering of the spins. You can have orbital order or an ordering of the orbitals. You can have so-called charge density waves where the charge distributes itself in a kind of a spatially modulated way, like ripples of sand on a dune. Again, breaking the symmetry of the lattice. So there are many, many different phenomena that can be realized. And one of the most popular one, as we, that we're, I believe, all familiar with, is that of superconductivity, which is perhaps one of the most exotic quantum matter phenomena that we know. And it leads to effects that cannot really be realized in classical systems. And one of them is the Meissner effect, which is the effect by which you have that a superconductor can levitate at a certain distance from a magnet. So it's important for applications, but also important for very fundamental science. And so in the modern field of quantum matter, we tend to distinguish between two main classes of phenomena. One is the phenomena that arise from strong interaction physics, so interactions between electrons. And one of the most basic models that capture this is the so-called Haber model, where we have electrons on a lattice that can hop around, so they have some kinetic energy to move around in the lattice, but they also have some interaction energy. And as a result of the balance of these two energy scales, we get a variety of interesting things happening. We have many-body physics, so we have many-body phenomena, collective electron phases, as I mentioned earlier, electronic symmetry breaking. We have electronic correlations. So if you decorate these long-range ordered phases with additional electrons or holes, then those holes and those electrons will not be able to move independently, but will have to move in a very, very special, coordinated, almost choreographed way. And then we have quantum entanglement as well, which is even a higher degree of exotica in this context. And then the other class of phenomena is electronic topology. And what we have with topology is we have that there is an emergent electromagnetism in these materials. So in other words, there are some pseudo-magnetic fields that appear not because there are any real magnetic fields inside the material necessarily, but because of the quantum geometry of the wave functions. And this is completely single particle physics, so there are no interactions involved. But these effects very much come from Berry phase effect. So the quantum mechanical phase that accumulates as an electron moves around in the solid and as its quantum wave function interacts with the other electronic levels in the solid. And so we have emergent gauge fields and the topological classifications of phases of matter. Various different classes of phenomena. I've mentioned a few already in the context of collective electronic phases. In the context of electronic topology, we have the quantum Hall effect, the quantum spin Hall insulator, 3D topological insulators, and so on. And really, even though at the first level we think of these two classes of phenomena as being sort of like distinct, essentially, there's a lot of things that can be realized at the intersection of the two. So we can get even more exotic physics, including the presence of Chern insulators, Kondo vial semimetals, topological Mott insulators, topological order. And the only catch, though, in the real world is that there are very few materials platforms that can host both topological and electronic symmetry breaking phenomena at the same time. So one of the core goals of my talk today is to convince you that this particular lattice that I will tell you about, this Kagome lattice, is one of the possible materials platform that can realize both these phenomena. And I will then focus in particular on one family of phenomena, which is collective electronic phases. So this is what the Kagome lattice looks like in real space. These are the atomic positions, and so these dots here are the atomic positions, and these lines are the bonds between the atoms. And the Kagome lattice is also known as the trihexagonal tiling of the 2D plane. It's called trihexagonal because it only contains triangles and hexagons. And it's the simplest form of tiling of the 2D plane that only contains these two particular shapes. As you will notice, some of you who are experienced with these kinds of systems will notice is that it's a lattice that belongs to the hexagonal system of lattices. And so it's a close relative of the triangular lattice and the honeycomb lattice. The triangular lattice only uses triangles. The honeycomb lattice only uses hexagons. But other than that, they have exactly the same symmetries. The only differences between these three lattices is that they have different number of atoms per unit cell. The triangular lattice has 1 atom per unit cell. Honeycomb has 2, hence the AB sublattice of graphene, for instance. And the Kagome lattice has 3 atoms per unit cell, A, B, and C, the 3 atoms on these triangles. Kagome lattice is very popular in Japanese culture. It's a very common basket weaving motif and also architectural motif. It's also popular in American culture, as it turns out. But what's really interesting about the Kagome lattice is its electronic properties. So if we take a different view now, if we start from the real space view of the real space image of the Kagome lattice, and now we go into reciprocal space where the electrons live, then the electrons live in a space, in a region of reciprocal space, which is called the Brillouin zone. So the Brillouin zone tells us where the electronic states exist, and there are some special points in the 2D Brillouin zone of the Kagome lattice, which is just a simple hexagon. That's just so the Brillouin zone of the Kagome lattice is just simply hexagonal, and there are 3 special points in this Brillouin zone. One is the gamma point at the center, where electrons have 0 momentum. And then there are 2 points on the boundary of the Brillouin zone, one at a corner, which we call the K point, and one at the midpoint of the edge, which is called the M point. And so if we now look at the band structure, so if we look at the electronic bands that exist in the Kagome lattice, and by electronic bands, I simply mean the set of energy levels for electrons as a function of momentum, we can look along these 3 high symmetry directions. So going from gamma to the corner of the Brillouin zone, so from the center to the corner, and then we crawl along the edge to the M point, and then we go back to the gamma point. And if we move along this particular path in reciprocal space, then we see that the electronic bands have these particular shape that you see in this drawing here. This is from a simple tight binding in assuming only nearest neighbor hopping, meaning the electrons only hop on a nearest neighbor bond. And so there are 3 main features to this band structure. One is the presence of Dirac fermions. So basically massless fermions that exist around the K point. Only around the K point you have these bands that are crossing each other linearly. So they have, at least in the limit of looking around the K point, they have 0 mass. And we have these regions where the band dispersion gets locally flat. So it rises, the band rises and then stops and then continues to rise in energy. And here is the same. So the band rises from the gamma point, and then it stops just for a little bit around this M point here, and then it continues. And then the third prominent feature of this band structure is the flat band at the top. So there's a completely flat band where all the electrons have exactly the same energy. And so if we look at the density of states, so if we count how many electrons exist as a function of energy in this band structure, we see that at the Dirac point, where we have the Dirac fermions, the density of states is vanishing. So there's essentially a vanishing number of electrons here. At the flat band, the number of electrons is diverging because all of the electrons have exactly the same energy. So we have like a delta function of energy in the density of states. And then at the Van Hove singularity, we have a divergent density of states because of the dispersion becoming locally flat. So now if we start from this band structure and we start to play with it a little bit, we can see how this band structure can be used to realize both topological phenomena and electronic symmetry breaking. So if we focus on these 2 points of the band structure where different bands are touching each other, and if we activate certain types of interactions, for instance, spin-orbit coupling or spin-orbit interaction, and if we also break time reversal symmetry, what will happen at these special points of the band structure is that you will have a singular source of Berry curvature, which is like a monopole of the pseudomagnetic field that is entirely due to the quantum geometry of the wave functions. And so this monopole of Berry curvature, what it will do is it will activate various different kinds of topological effects that have been seen in a variety of these Kagome-based materials. So we have Chern physics, where we have essentially something that behaves closely to a quantum anomalous Hall insulator. We have magnetic Weyl fermions, and we have this topological flat bands as well. So this topological effect essentially arises from breaking the generacies in this band structure. So where we have bands that are touching each other, if we can break the degeneracy between at the band touching points, then we can potentially activate these topological effects. If we play with filling control, so if we imagine that hypothetically we can move the chemical potential anywhere we like in this band structure, and if we place the chemical potential at one of the places where the density of states is diverging, so the flat band or the Van Hove singularities, then what will happen is that the system will not like to have a high density of states at the Fermi energy. And what we will tend to do is it will tend to break some symmetries in order to remove that degeneracy. So breaking symmetries, opening up a gap, splitting away the regions of high density of states and leaving a lower density of states at the Fermi energy through a mechanism which overall lowers the total energy of the system. So it's energetically convenient for the system to do so. And this has been shown to happen in a different class of Kagome materials, which is what I will talk about today, where a variety of symmetry breaking phenomena, a remarkably rich variety of symmetry breaking phenomena has been observed, including superconductivity, charge density waves, pair density waves, which are essentially density waves of Cooper pairs, nematic order, so breaking of rotational symmetry, orbital magnetism. There's really quite a garden variety of things that happen in these systems. And so this is what I will focus on in the rest of my talk. So if we look at this family of materials, this AV3 antimony 5 systems, or also known as the 135 Kagome metals, this is the structure. So of course the materials are not 2D; they're really 3-dimensional. So all materials that we work with are bulk materials, so they're 3-dimensional in nature. And so if you look at the view from the side, you'll see that you have these alkali atoms. In this case, this is cesium. And then you have this network of vanadium and antimony atoms that are coordinated to each other in a certain way, in a certain pattern. And if we look from the top, if we look at this unit cell from the top, we immediately see the structure of this Kagome lattice formed by the vanadium atoms. So the vanadium atoms form these Kagome lattice, which can be seen very clearly if we look from the top. And so effectively, we can think of this system as being formed by a layering or a superposition of different Kagome layers. So the Kagome layers are the building blocks of this material. This material exhibits superconductivity at a relatively low temperature of around 3 Kelvin. And it also exhibits what's known as a charge density wave below a temperature which is a bit higher, is of order 94 Kelvin. And the charge density wave can be seen in transport. So you see an anomaly in the resistivity, and that signals some kind of symmetry breaking transition, in this case, the charge density wave. But it can also be seen in diffraction. So you can probe it directly in reciprocal space in the Fourier domain. So the charge density wave phase manifests itself through the appearance of some superlattice peaks in the diffractograms of the material. So what is a charge density wave? Fundamentally, how do we characterize a charge density wave? So you can think of a charge density wave, as the word says, as a spatial modulation or a static wave, a standing wave, if you like, of charge density, of electronic density. And one that breaks the symmetry of the lattice, because of course we know that the electronic density is periodic, has the same periodicity as the atomic lattice. But when that periodicity is broken, when the electrons organize themselves with a period which is different than that of the lattice, then we talk about a charge density wave. And so we can have this gentle modulation of the electronic density as a function of the position on the lattice in one dimension at least. Or we can have, similarly, a distortion of the lattice. And a distortion of the lattice will cause also a modulation of the electronic density in the system. Now, in 2D, things are relatively simple. There's not really many configurations for the charge density wave. It's just a one-dimensional modulation of either the charge density or the lattice displacements. In 2D, things are more complicated, but also therefore more varied and more rich. And if we look at the Kagome structure, this is the pristine unit cell of the Kagome layer. It's this small rhombohedron you see over here. And this is the undistorted Kagome lattice. But if we create a charge density wave on a Kagome lattice, there's two different types of charge density waves that can appear, or two different patterns of reconstruction. One is called the Star of David, where essentially the bonds that are drawn in blue here, they shrink, they become smaller. So all these triangles here on the Star of David pattern, they become smaller. And the other one is so-called the trihexagonal, where you have that the unit cell essentially breaks into hexagons that become smaller in size, so they collapse a little bit, and triangles on the two sides that also collapse a little bit. And so the phenomenology of these Kagome metals is remarkably rich. You have this charge density wave or charge order transition at 94 Kelvin, but then you have this loop current order happening at a lower temperature, uniaxial stripe order, electronic nematicity, so breaking of rotational symmetry, and then at the lowest temperatures you have superconductivity. And all of these things happen in the very same material. So there is this cascade of phase transitions that happen in the same material, and what sets the stage for all of these phase transitions is really the first symmetry breaking transition that happens, which is the charge density wave. And so Kagome metals are sort of right there in terms of playground for quantum matter physics, are right there with some of condensed matter physicists' favorite platforms for quantum physics, which is the copper oxide high temperature superconductor, iron-based high temperature superconductors, as of more recently the magic angle twisted bilayer graphene and all these moire superlattices, etc. Okay, so the question that we asked ourselves, and I'm realizing maybe I should speed up a little bit now, is does the electronic band structure of the Kagome hold any insights into the origin and the nature of the charge density waves in these systems? And so, as I mentioned earlier, the places where we would want to look for, driving forces for symmetry breaking transitions are places in the electronic structure where the density of states is high. So one place would be the flat band, where the density of states is diverging. But two other places of interest are the two Van Hove singularities. So these two settle point-like dispersions at the endpoint. And if we look at these two Van Hove singularities, that, as a function of two-dimensional momentum, so not just as a function of one-dimensional cuts in the Brillouin zone, but really as a function of 2D momentum. And we see that they have this kind of very characteristic settle point-like dispersion, where the dispersion of the bands is concave along one direction here and is convex along the perpendicular direction in the case of the upper Van Hove singularity. And for the lower Van Hove singularity, it's essentially rotated. So we see a concave dispersion along this direction, which is K point to M point to K point. And then along the orthogonal direction, so from gamma to M back to gamma, we see a convex dispersion. So this is the expectation, the simple expectation based on a tight binding model of what would happen on the Kagome lattice. Now, if we do DFT, density functional theory, to understand the electronic bands in the real system, so by inputting the real structure of the system, then the reality comes out to be actually quite different. So this system has many electronic orbitals that are involved, and they form multiple bands. Those multiple bands tend to overlap, and so it's quite a jungle of different bands in the so-called spaghetti plot, which is what's shown here. But in particular, you will notice that there are 3 bands that seem to all have these Van Hove singularities, or these locally flat dispersions near the Fermi energy, near the chemical potential, which is where we expect that a pileup of density of states would drive the system unstable towards a broken symmetry phase. And so we see mainly 3 bands. I'll go quick through this, but we see bands that have different orbital character that form Van Hove singularities near the Fermi energy. So how do we measure the band structure? So the technique we use is angle resolved photo emission. I presume most of you are familiar with this technique. It's a modern version of the photoelectric effect that was discovered by Hertz and explained by Einstein. So you shine ultraviolet photons onto a sample, you photo eject electrons, you collect these electrons in the so-called electron analyzer, which can measure their angle, their takeoff angle, and their energy. And by just simply applying energy and momentum conservation, you can map out the electronic levels or the electronic bands as a function of both momentum and energy. And this is here as a 3D volume plot of what this looks like in a particular material, in this strontium ruthenate, where you see the electronic bands as a function of energy, but also you see their shape as a function of momentum. So if you now look at how things look at the Fermi energy, so we look at the Fermi surface, or where the bands are at 0 energy, we see that there are different bands as expected. The hexagon here is the Brillouin zone. And so I want to highlight the points that are important here to consider, which are the gamma point in the middle, and then the K point at the corner here, and the M point here. And really, what the physics we're interested in is to understand what happens around the M point, where we expect these saddle point dispersions here. So if we look closely in the DFT at these dispersions, and we kind of look at along 2 main directions, so the K point to M point to K point direction, which would be this direction here in this plot, and this direction here in this plot. You see that one type of Van Hove singularity forms a top, and the other one has a bottom. Whereas the opposite happens if you look along the perpendicular direction. So the bands that would have a top over here, they now have a bottom in the dispersion over here, and conversely, the red band that had the bottom over here in the perpendicular direction has a band top. And we can map these out in great detail with angle resolved photo emission. We can see these bands as a function of momentum and as a function of energy. We can see this band top, which is this locally flat dispersion that forms a Van Hove singularity. And the really intriguing thing is that if we look at these at high temperature, we see that, so above the charge density wave transitions, we see that these bands have essentially this Van Hove singularity almost perfectly at the Fermi energy, which is where we expect the system to become unstable towards symmetry breaking. And as we lower the temperature and we enter the broken symmetry phase, what we see is that these bands get pushed down, get renormalized in energy by a massive amount, which is of order 80 milli-electron volts. So there's an energy gap that opens up at the Van Hove singularity, which is as large as 80 milli-electron volts, which is something which is in units of kBT/CDW, so the thermal energy for the charge density wave transition is of order 10. And 10 is a big number. That means that the electrons are strongly coupled to some other degree of freedom. So I'm almost done. I'm going to wrap up now just to show one last thing, which is what happens if we now take the density functional theory, we take the electronic bands that we calculated, and we artificially distort the unit cell in the way that we expect to happen at the charge density wave transition. And so if you progressively distort the unit cell, you see that these bands just at the end point, at the Van Hove singularity, gets pushed down by a very large amount of order hundreds of milli-electron volts. And so what we're witnessing essentially is the fact that these degeneracies at the end point, at the Van Hove singularity, are being removed by the lattice distortion. And this happens because there's very large electron lattice coupling at play in this system. And so to summarize, so we see these singular electronic bands that have these enhanced density of states at these Van Hove singularities. We see them very nicely in the experiments. We see these saddle point dispersions, and we believe that this is what really enables all of the exotic physics of these collective electronic phases in this class of Kagome materials. And that's all I have, and I'll be happy to take questions.
new physics, very just in a material, in one material. Actually, you have all these three bands, three structures, and yes, I mean, people. I think questions are coming. Maybe I can ask you a very naive question. So you were speaking about the twisted graphene structure. I mean, a structure that provides superconductivity, many features. So is it possible to have your Kagome lattice as just a double layer of an hexagonal and a triangular lattice?
Oh, that's an interesting question. Actually, I thought that what you were going to ask was whether we can get a truly 2D Kagome layer, which maybe I'll get to later. But no, I don't think we've ever thought along those lines to actually superimpose a honeycomb and a triangular lattice. Although, if you could do that, I mean, at least mathematically that would work. So you could indeed form a Kagome lattice by superimposing the two in the right way. Let me just get to the right slide so illustrate that. Yeah, so indeed, the one could potentially form the Kagome lattice by taking the sublattice of a triangular lattice and put it together with the two sublattices of a honeycomb lattice. The complication would be that they wouldn't be exactly on the same layer, so you would still have a honeycomb and a triangular lattice bilayer, as you mentioned. But it could be that some of the physics, as far as the electronic band structure is concerned, could be similar to what we see in the pure Kagome lattice. So I don't think this has been explored. So it's actually a very interesting proposal. Like what we're really dreaming of is to be able to find a 2D Kagome lattice. And so realize like the version of graphene, which is a 2D honeycomb lattice in the Kagome system. Because then we would have access to essentially the exact same physics as graphene, because we have the exact same electronic bands as we have in graphene, especially the Dirac fermions. But on top of that, we would have the flat bands. We would have a lot to play with if we had really truly a 2D Kagome layer, maybe something that can be functionalized into a microelectronic device or something like that.
So we have expertise in the institute about the surface-driven polymerization. I mean, maybe this could be a way to make a synthetic material driven by the surface. Maybe this could be a point of discussion. Thanks.
Yes, I believe that the Kagome lattice has been realized in some systems through self-assembly or through other mechanisms. And it's been observed, I believe, also in metal organic framework. So it seems to be a kind of lattice which is quite ubiquitous. It's not just something that exists for atomic scale systems, but it can be, it can be scaled up in some ways. Yeah.
Okay, so I think let me check on the different channels. Now I think the people thanks for very impressive presentations. No, there are no other questions. So then I invite all the attender to directly ask questions to Riccardo. And I believe now let's move to the award ceremony. I just switch on my my presentation. Just a second. And exactly. Okay, so I'm really glad to award with the PRISM 2022 senior category Riccardo Comin for the breakthrough achievement in the past 5 years in the field of science of materials. Congratulations, Riccardo, because you are really pushing the knowledge in the field of structural matter beyond the state of art, and you are doing right now in the last 5 years. It's not a career, but I mean, it's really a running prize because you are doing right now this discovery and this breakthrough discovery to push our knowledge beyond. Thanks really a lot and congratulations. You see the prize, which is just a symbolic prize, and also the pergamena that will ship to you in MIT. And as I said, I mean, we offer you, I mean, a collaboration activity supported by the Institute in the topic you were just mentioning. So I think there would be could be a very fruitful collaboration in the future. Thanks a lot, and congratulations again. Let's move to the next. I'm really proud to award the PRISM 2022 the junior category to Stefania Cacovich of CNRS in France, and for the breakthrough achievement she did in the past 5 years in the field of science of materials. Thanks a lot, Stefania. You were showing that, I mean, it's possible to have innovation, breakthrough discover in a field that is also going in the direction of sustainability, which is very important as well for our future. We are very happy to give this prize to you, and as you see this, we have the prize, which is something like that. Sorry, and then we have we will ship this prize to you together with the pergamena. And as you're already doing so, we are really happy to have a fruitful additional collaboration with your team in the next years in the topic you were showing. Okay, so Stefania already knows ISM, so we have some collaboration. We can even expand this kind of collaboration together.
Sure.
Congratulations! Thanks really a lot for your activity and for your to push the knowledge beyond the state of art. Thanks a lot, Stefania.
Thank you.
Okay, so we are at the end, and really I thank all of you and also the people that were attending the streaming online. And I invite you to be part of the 2023 PRISM Prize as a jury. And I believe in a few months we will open for nomination, and then the jury just after the selection, just after the summertime. So it was really a pleasure. Congratulations, and see you soon for a collaborative research. Bye.
Thank you.
Bye.
Bye. Bye.
Bye.
Bye.